We continue our discussion of motion. So here you see the cars. This car moves at constant velocity. This one moves at constant velocity. So with a specific periods of time, it's the same velocity, no changes. This one has a constant acceleration, so the acceleration is constant, but when you add the acceleration to the velocity starts increasing and increasing and increasing. This is what happens when we drive our cars. The acceleration is constant, but the velocity will be increasing, because each second you are adding to it more velocity. This car has a constant acceleration in the negative direction. This is slowing down. So originally was like this, the velocity, the acceleration is opposite. So now the velocity is reduced. After a third second, the velocity is reduced further. Fourth second, reduced further, and so on and so forth until it stops. So I hope that these graphs help us to understand this game very well. Check your understanding again. The three graphs in the figures below represent the position versus time for objects moving along the x-axis. So the motion is along the x-axis. Which, if any, of these graphs is not physically possible?
Would it be B?
Okay.
I think it'd be B.
Yeah. Very well. This figure is a diagram of a multi-flash image of an air puck moving to the right on a horizontal surface. Okay. The images sketched are separated by equal time intervals, and the first and last images show the puck at rest. In the graph, which color graph best shows the puck's position as a function of time? What would you say?
Blue.
Which one?
Blue.
Yes, I will buy that, because here the change in x with time is almost constant. This is what we have in the blue line. The green line, we don't have changes, so I will remove it. And this one looks like a curve more than a straight line, so I will prefer this one, the blue, yes. Thank you. In the figure, which color graph best shows the puck's velocity as a function of time? So now we are talking velocity. So here, the velocity with time is almost constant. So
Red.
I will, yeah, no, I will not pick this one. Okay, yeah, the velocity is constant. Red here, velocity is constant. You are right. Here it was accelerating, positive acceleration. Yes, this is positive acceleration. Then constant, and then it slowed down. Yeah, the red would be the best. Thank you. Which color graph best shows the puck's acceleration as a function of time?
I say green.
So this is the acceleration. So here it was constant. Here it dropped to 0. If you want to take the green, it does not drop to 0. It's still moving up. So I will not pick a green, no. In fact, there is continuing slight change, so I'll pick the red again, right? Because here it starts from 0, moving up. That's the case with the red. Then here still going up, but at a slower rate compared to the first rate. So it's went down, and then it starts slowing down, so it will follow this path. You buy that? Okay? Very well. So for motion with constant acceleration, this is a motion with constant acceleration. The acceleration value does not change with time. This is the time axis, and the acceleration is constant. Therefore, the slope is 0. The slope for this line is 0. On the other hand, the velocity, when you have constant acceleration, it will be increasing steadily with time according to this straight line, because the acceleration is constant. The acceleration is constant. The slope is 0, but the acceleration is not 0. It has a positive value. It's important to understand and digest these concepts. Once you feel comfortable with them, that's it. You are now a professional. You understand this whole game. Okay? So acceleration is the change in velocity divided by the change in time. You need, in order to calculate the value of the acceleration, you need the final velocity, you need the initial velocity, the difference divided by the change in time. So this way you get the acceleration. We are assuming the initial time to be 0 here, so t is the same as t final. So from this equation, if you multiply by t both sides and rearrange the variables, you get v equals v naught plus at. In plain English, the final velocity is equal to the initial velocity plus the acceleration multiplied by time. Okay? This is how we calculate the final velocity for any motion, if we know the initial velocity and if we know the acceleration and time. This is one of the 4 kinematic equations. And here you see it is emphasized that the acceleration is constant, because if it wasn't constant, the math involved would be too complicated and we would get the level of this course. We don't need that. So here, the initial velocity was 2 meters per second. It's not 0. This is the velocity axis. It was 2 meters per second. Okay. And the acceleration was 6 meters per second given to us. We are interested in calculating the final velocity after 2 seconds. The final velocity after 2 seconds. We use that kinematic equations. Final velocity equals initial velocity plus at. Initial velocity is 2 plus the acceleration is 6, and the elapsed time is 2 seconds. Evaluate this expression, it is 14 meters per second. So now we are educated. We know how to calculate the final velocity if we know the initial velocity, the elapsed time, and the acceleration. That's nice. If the motion has initial velocity v naught and final velocity v, then the average velocity, you add these 2 velocities and divide by 2. Just like if you scored 60% in one exam and 80% in an exam, the average would be 60 plus 80 divided by 2, which is 70. The same kind of game. Okay? So this is another way to calculate the average velocity from knowing the initial and final velocities. Also, the average velocity as we defined it before it is delta x divided by delta t. Okay, so from this equation we get delta x equals the average velocity multiplied by t. Here we are assuming the initial time to be 0, so the final time and t is the same. Now I take this expression for the average velocity and plug it here. So it is v naught plus v over 2 multiplied by t. So I have the second equation of the kinematics equation. We have 4 of them. So this is the second kinematic equations. The change in position x is half v initial plus v final multiplied by t. Again, this is for constant acceleration. Now, if we substitute for the final velocity from the first kinematic equations, v equals v naught plus at, if we substitute here and do some algebra, so now we have x equals half v naught plus v naught plus a. So it is 2 v naught multiplied by t divided by 2. So you end up with v naught t. 2 cancels with 2. And then you have at multiplied by t. So it is at squared. And you have 1/2 here. So you end up with x equals v naught t plus 1/2 at squared. This is the third kinematic equation. Okay, this is the third kinematic equation that allows us to calculate x if we know the initial velocity, if we know the acceleration, and if we know the elapsed time, we can calculate the change in the position x. Okay, and as you can see here, the change in x with time is parabolic because you have t squared, not only t. If it was only t, it would be straight line. But because you have this parabolic term, power 2 term, okay, then the curve, this red colored curve, will give us the value of x with time. Okay. So the change in x, v naught t plus half at squared, we can calculate that as also the area under the graph of v versus t for any object is equal to the displacement delta x of the object. Very well. Now back to the first kinematic equations, and now we will solve for t. T is v minus v naught over a. So here we substitute for t this value, v minus v naught over a. We simplify. 2 multiplied a is 2a, and this is v naught plus v multiplied by v minus v naught will give us v squared minus v naught squared. We can write this formula as v final squared minus v initial squared equals 2ax. This is the fourth kinematic equation, again at constant acceleration. So now we derived the 4 equations that we will need to do kinematics. You see the summary here. This is the nice summary for the kinematic equations. This is all what you need to solve motion problems. Okay. These equations, and the fourth equations is delta x equals 1/2 v initial plus v final divided by 2. Okay. Multiplied by time, sorry, 1/2 v initial plus v final multiplied by 2. That is the fourth equation. This one, okay. Very well. To solve problems, this is the strategy that I think should work always. You need first to understand the problem. This is very important. Don't rush to solution before understanding the problem. It helps you to understand the problem if you sketch a diagram sketch a diagram, label all quantities, read the problem several times, not only one time, extract the information, label the drawing that you need, then choose the correct equation of the kinematic equations, plug in the numbers and solve for the unknown. The last step, check your answer. Does it make sense? Okay.